Okay, folks, so we're going to pick up on 8.10 part 2, and I have a lot of information already written out on these, so I thought that would be good just to kind of scroll through and discuss it and make the video a little shorter, and you can then pause it where you need to. So in this section, we're going to do some approximations, and we're going to look at the nth degree Taylor polynomial. Of course, you see that where it's centered at C. You have that definition. And then in the box, then you have it's called, oh, by the way, just a couple things here. There. Okay, so you have that it's called the nth degree Taylor polynomial for the function f of x at C, and it's named after Brooke Taylor, an English mathematician. Then if C is equal to 0, then the polynomial is equal to f of 0 plus f prime of 0 and so on. And that's called the nth degree Maclaurin polynomial for f, named after the English mathematician Colin Maclaurin. So we've already done a little bit of work for this, but I start off and I find the third degree Maclaurin polynomial for e to the x. And remember that we had already done this practice, so I'm going to leave it up to you, the reader, or the listener in that case. So the polynomial of the third degree. Okay, and then I'm going to use that answer. So here's where we very often have to put our series into another expression. So I put it in as 1 plus x squared over 2 factorial plus x cubed over 3 factorial minus 1 as the function has it, only replacing just the f of x here with this expression. So there we have it. And then if we take the limit then, we're going to manipulate this thing, right? So I would say probably if you put 0 in, you know what's going to happen. You're going to have these two terms cancel, right? The 1 minus 1. So you're going to simplify this, and let me make it just a little bit smaller. Let's kind of see what I have under there. So we then have the limit as x approaches 0 of 1 plus x over 2 factorial, if you will, plus x squared over 3 factorial. And I'm just going to leave the 2 there. So I just canceled the x if I have the 2 in the denominator. So if you see, when you plug 0 in the two terms, you're going to get the limit is equal to 1/2. Okay? So that's it for that one. So now just a reminder of what the Taylor polynomial is right there to have it just above, f of 0 plus f prime of 0, x, and so on. So suppose that the function f of x is approximated near x is equal to 0 by a third degree Taylor polynomial. So this polynomial, p of 3 is equal to then 2 minus 5x squared plus 8x cubed. So the first thing I want to find the value of f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So right off the bat, I know that f prime of 0 is going to be 2, because it's the constant that I have to achieve there, the constant value of the Taylor polynomial and that first term. So f prime of 0 is going to be 0 because there's no linear term. There's no x term there. It goes right to the x squared term. Okay. So I'm going to skip up then. I'm going to say f double prime. Well, I know that f double prime of 0, let me use blue. F double prime of 0 is not known yet, but I know the whole term is f double prime of 0 x squared over 2 factorial. So I know that that has to equal that x squared term, negative 5x squared, right? So then f double prime of 0 over 2 factorial, or just 2, is equal to then negative 5, just dividing out by x squared to see. So then I know that f double prime of 0 is equal to negative 5 times 2 factorial. Kind of like to stick with the notation there, but it's still just 2. So we know that that f double prime is then negative 10 here. Now, there's a real matchup with this. Remember that you want the series to be equal and behaving the same as the function. So the third derivative, then we can see that the term is 8x cubed. And then we see that f triple prime of 0 over 3 then is then going to be 8, okay, dividing out by x cubed. And then f triple prime of 0 is then 8 times 3 factorial, and that's equal to 48. Okay, so you have the first answer. Now, I just did a little aside with you here just to show you that if I take the derivative of the polynomial, you can kind of see that I get 0, -10, and 48, and they have to match up. Okay, so this is kind of a good skill to have for those questions that say, what's the coefficient of the x squared term going to be? Or so just to figure out what is f triple prime of 0 given the polynomial. All right, and then the second one, just going over this briefly, I hope that was clear enough there. Does f have, it almost seems like it's so simple, but necessary to explain. Okay, does f have a local maximum, a local minimum, or neither at x equals 0? The thing about this problem, it's kind of ambiguous when you first read a question like this, but remember, we have f prime is equal to 0, right? The first derivative test would say that, okay, well, we know the derivative is equal to 0, but there's not enough information about what happens on either side of 0. So I drew you a number line here and said, for example, if f prime went from a positive to a negative, where f was increasing or f was decreasing, we would have information that would tell us that, oh, it's a maximum at that point. We don't have any of that. But what we do have is we have the second derivative test. We know that f prime of 0 is 0, so we have a horizontal tangent. And then we know f double prime of 0 is equal to -10, and that means f is concave down. So remember, by the second derivative test, and I could list all the parts of it, but I'm kind of out of room there, and you can look up the second derivative test if you need review. Then we can conclude, do I have room for this? Therefore, f has a local max at x equal to 0. Okay, and that's because if the graph is concave down, you know, when the graph is concave down because the second derivative is negative, then that horizontal tangent being right there would mean that you would have a max at that point, okay? All right, remember, if the second derivative is equal to 0, the second derivative test is inconclusive, all right? Then we go on to a familiar problem having to do with finding 8th degree Maclaurin polynomial. You guys know how to, the 8th degree. I guess I have a little more to do there. Okay, so find the 6th degree. Why did I have 8th degree? I retyped this and I think I only want the 6th degree. Let's change it, 6th degree. You could do a couple other terms, but not necessary. So you go through the process where I wrote them all down, even though you know once you get to sine, it's just going to repeat cosine, negative cosine, and so on. But if you look at this, you have the 6th polynomial, you have the linear term, the cubic term, and the 5th degree term all go to 0 because their derivatives are equal to 0. And you end up with a 6th degree polynomial that you see here. Okay, just a little. Now, in this case, using your answer to approximate the value of the integral from 0 to 1 of 1 minus cosine t over t squared, so that the error approximation is less than 1 over 500. So you set it up to integrate, okay? And what you're going to do is take this polynomial we just got in terms of x's, p of x, we're going to make it a p of t, and we're going to plug it in here. So once we plug it in this step, then we're able to simplify, okay, canceling the ones. Of course, we have this 1, change it to addition of the opposite, so you get all your signs right. Make sure I get my signs right. Okay, you end up here where now it's simplified in the numerator over t squared, and then I simplified the entire integrand. Now keep in mind, we are looking for error. Notice I have 3 terms there, and I'm using the answer to approximate, and I'm going to use that last 6th degree term in the integral to see if it's enough error to satisfy the 1 over 500. So here we integrate, simplify. Remember that you have polynomials that have t in them after you integrate. So when you plug in 0, it's just 0. So it's actually a minus 0 here. Here's the evaluation of the integral at 1. Okay, simplified. So you get this 35 over 72 plus I left the last term as 1 over 5 times 6 factorial. Okay, so note that this is an alternating series and it's decreasing. The terms are decreasing. T squared gets pretty big. 1 minus cosine t goes from 1 minus a negative 1, so the numerator will be from 0 to 2, right? So over t squared, so it's going to get smaller and smaller and smaller. And so it's alternating, it's decreasing, and the limit as n approaches infinity is 0. So the error, so it's going to converge, but the error then would be that next term. So if I only use the first two terms, these two terms, to approximate it, where am I here? These two. And then I'm going to call this my remainder for the error by the Taylor theorem, Lagrange remainder, if you will. All right, so what I do then is I say, well, the error, I want it to be less than, down here at the bottom now, I want the error to be less than this, right? So error less than 1 over 500 is equal to 0.002. Now, I got to get my calculator out to see what that is. I thought I wrote it down here. So 1 over, well, it's definitely less than, I don't really need to calculate it. I know that 1 over 5 times 720, that last term is what that turns out to be. This one, this term here turns out to be equal to this. So in that case, then it's definitely going to be less than 1 over 500. So we know then for our answer, we know that the integral from 0 to 1 of cosine is going to be approximately 35 over 72, and with an error of less than 1 over 500. Okay? I'm going to go to this last one, see if I can get through that one, because the last part of this says we want to use our calculator to find the actual value of 1 minus the integral of 1 minus cosine over t squared from 0 to 1. Now, there's a little problem with this because it's an improper integral, but you can kind of get through it to get the answer, and I'll show you how. So the estimate we got was this, and the error, oh, here it is. I knew I wrote it down somewhere. The error turns out to be very small and doable, less than 0.002, right, or 0.005. I forgot what it was, 0.002. So it definitely turns out to be less than that, so we're good there. And then the actual value in the calculator, remember this is an improper integral, so you got to kind of cheat your calculator. So what I did when I did Math 9, I put in the integral and I put the 1 in up top, and then in the bottom I put a 0.0, you can put 0.001. I think that's what I put, and then I was able to get something like 4857, I think, something like that. You can check for yourself. So it comes out to be extremely close. You can see the error is out to the 4th digit there, so not really a huge problem. All right, and that's it for today. I'm sorry I had to take off and take a half day today, but I will see you on Monday. If you have any questions, please ask me. Best to all of you. Take care and keep looking up.